Welcome back, students. So in the previous lecture, we looked at strain hardening mechanism, and we looked at the relation given by Taylor hardening relation, which says that shear strength is proportional to under root dislocation density. So here the assumption was that as we increase the deformation and the strain, dislocation density is increasing. So how does the dislocation density increase when we increase the strain? So we will today look at that aspect, dislocation multiplication and related to it intersection and dislocation locks. So that is the purpose, that is the objective of the lecture. So let's look at dislocation multiplication. So the dislocation multiplication mechanism, which is one of the mechanism which is very well known and widely accepted, is the Frank-Reed mechanism. So what this mechanism is saying is that, let's say you have a dislocation which is pinned at 2 points. So in here you have a dislocation like this, and these 2 points are pinned. And the rest of the dislocation must exist somewhere else. So this is only part of the dislocation, and we are only looking at the region in between these 2 pinned points. Now, if you apply a stress such that the dislocation has to extend in length, therefore it will look like this. And if you keep applying the stress, then the dislocation would loop like this. And you keep applying the stress, then eventually it forms something like this. And then you can see already that the dislocation length is increasing. Okay, so as we are applying more and more stress, leading to more and more strain, the dislocation length is increasing. But that is not all. You would see that it multiplies even further. So at this point, what will happen is that these are in opposite. The Berger vector over here, or sorry, the line vector here is in opposite direction. And therefore there will be attractive force, and therefore these two will merge, and what we will get is something like this. And if there is a grain, then this dislocation would move on, and the stress would keep acting on this part of the dislocation, and therefore this will again form a loop, and it will keep on forming a loop. And there is a very nice animation which shows this particular mechanism and how it leads to pile up. And this will clearly show you when you are applying strain, when you are applying the stresses, the strain is increasing, and which in turn leads to increase in the dislocation density. So here you are looking at this. These are the 2 pinned points, and there is one grain. This has been shown over here, and you can see that this forms a loop. And then again, since you are applying a further stress, you can see that it is again forming a loop, and this part remains over here. So it acts like a source, and over here it keeps on forming new and new loops. And if you look at this cross section, what you would see is a pile up. So this is the grain boundary, this region, and these are the dislocations which are piling up near the grain boundaries, and the distance is increasing, and you would see that new and new dislocations are forming, and it keeps pushing. So every new dislocation that forms, you will need even higher and higher stress. This is what we said, and is very evident from here. So this clearly shows, or this animation clearly shows that what we had said earlier, that with increase in the stress and when the strain increases, dislocation density increases. And this animation was able to show that very beautifully. Now, if in a grain, you may have even some more type of obstacles. And when you have a source like this, it would lead to even higher increase in dislocation density. So here these are like precipitates, and here you have somewhere here you have a source, and as you are applying stress, these stress are causing the dislocation to become loops, and the loops keep on going, and it is forming loop around the precipitates also, and therefore a new dislocation is formed around the loop, and all the loops, sorry, a new dislocation loop is forming all around all the dislocations, and the original dislocation still keeps appearing over here, and it leads to even higher increase in the dislocation density. And we know if the dislocation density increases, then tau is equal to alpha GB under root rho. So higher the dislocation density, higher will be the shear stress required for every new dislocation. So this mechanism clearly, this is clearly a very well-established mechanism for dislocation multiplication, and shows that higher stresses lead to higher dislocation density. And Taylor hardening has already established that strengthening with increasing dislocation density. And in these two, we have seen clearly dislocation pile up leads to strengthening. So these two animation have further corroborated our what we said, that the dislocation pileup leads to strengthening. Now that we are talking about dislocation multiplication, it is proper to also state that there are other mechanisms of dislocation multiplication, although they are not as frequent or as probable, particularly from the point of view of material processing. So what are these? So for example, due to accident growth. So other mechanisms for so it may be, for example, when you are doing crystal growth, at that time there is because there may be stacking sequence fault, and because of that because of those faults there may be dislocation that may get generated. So due to accidents, it is as it is called, due to accidents in crystal growth. Now, dislocations can also be nucleated by homogeneous nucleation. Just like the nucleation of precipitates, there is also possibility of homogeneous nucleation of dislocation. But the stresses required are again very high. So it is not very probable. And there may be stress concentrators in the crystal that can lead to dislocation generation, like the mechanism which was proposed by Cottrell near the pileup of the dislocations. that there is a stress concentration which will lead to source generation in the neighboring grain. So that kind of stress concentrators can also aid in dislocation multiplication. And if we look at the dislocation multiplication, then if you, from one of the books by Dieter, you would see that by just deforming a material by few percent, so if you are applying a strain of few percent, the length of dislocations become as high as 50,000 kilometers in each cubic centimeter. So just to put it in perspective, metal which has been plastically deformed a few percent, not even severely deformed, in strain contains approximately 50,000 kilometers or more dislocation line in each cubic centimeter. So that is the effect of dislocation multiplication when you are doing the deformation. So if you have done just a few percent straining of the metal, then dislocation length in that would be inside the material would be of the order of 50,000 kilometers. And you can imagine the effect that it will have on dislocation density and hence the strength of the material. So this is dislocation multiplication, and what we observe here is that one way or the other, the dislocation must get pinned to give this kind of mechanism, Frank-Reed mechanism. So this also gives us the question of why at all would there be a pinning of the dislocation. So we can look at some more mechanisms which lead to this kind of pinning. So in this respect, let's look at dislocation intersection. Now, dislocation intersection in itself is a mechanism which would lead to strengthening of the material, because you are causing a step in the dislocations, as you would see when we look at in more detail. And because that is extra step is created, which requires extra energy, therefore overall higher stresses are required. Now, at the same time, some of these steps that are formed are sessile in nature, meaning they do not move. And if they do not move, it means that the rest of the dislocation will have to move, but these will not, this will remain pinned at that place. And hence you can have that kind of Frank-Reed source where some part of the dislocation is pinned and the rest of it is looping around and giving rise to a higher and higher length of dislocation. So let's try to get an understanding of dislocation intersection. So two straight dislocations can intersect, and when they intersect, they will leave behind jogs and kinks. Now, these extra segments in a dislocation line cost energy and hence require work done by external force, which is where we would mean that we need extra stresses to be applied, or in other words, there is hardening of the material. So we will also look at what this extra energy cost means. Implies hardening of the material. Now, the simple rule when an intersection is formed is that the size of the step is equal to the magnitude of the Berger's vector of the other dislocation. So this is the rule based on which we will be able to find out the size of the step and the Berger's vector. So Berger vector, of course, Berger's vector will never change. It will always be same for the as for the original dislocation, and the size of the step would be equal to the magnitude of the Berger's vector of the other dislocation. Now, in order to explain this, we will take examples of 4 different types of intersection. So first we will look at edge dislocation, where the Berger's vector are in perpendicular direction. So let's say we have one plane like this, and the other plane like this. Now over here, we have a dislocation line like this. And for the sake of, for this one, we are assuming that both of them have edge dislocation. So this is the edge dislocation over here. And this is the edge dislocation over here. And let's say that this one is moving in this direction. And over here, the Berger's vector for this one is like this. So this is Berger's vector 1, B1E, and this is B2E. So now this is moving. So at some point it will intersect here, and then it will keep on moving. So how does it look like? That is the question. So first again, let's draw the 2 planes. And over here, okay, so I have made a mistake. This will not be anymore like this. This will actually be now 2 planes, and I will explain in a moment. So this is intersecting or attaching to the original plane over here, and this one over here. Now, this particular dislocation has Berger's vector like this, which means the step formed on this will have a magnitude, will cause a step with a magnitude of Berger's vector B1 on this direction, which means this will be the step that will be formed over here, and it will look like this. So So the intersection results in a step whose size is equal to the magnitude of the Burgers vector of the other dislocation. And so that size is equal to B1. So this size is B1, and also it is in the direction of the original Burgers vector. So the other thing that I forgot to mention here, and in the direction of other Burgers vector. On the other hand, for this one, the step will be created, which will be equal to the Burgers vector in this direction, and also equal to the magnitude of this Burgers vector. And in effect, that would mean that we will have one step. So it has moved just one step in this direction, which means that nothing has happened to this particular dislocation. On the other hand, this one has caused a step over here, which is jog in nature. You can see jog meaning it has left the original plane, and it has, therefore there are two different planes, and the Burgers vector remains like this over here. So this is the line vector and this is the Burgers vector, therefore this is still a edge dislocation. So this is S2 and there is S1. Just theoretically speaking, there is not much actually happening for S1. So if we want, we can write it like this. S1 magnitude is equal to so we are calling the step S1, which will be equal to the Burgers vector B2. And the B2 is over here in this direction, which is in the line direction for this. And therefore, it implies no change for this, for dislocation 1. On the other hand, for S2, the step size is equal to Burgers vector 1, and also the step S2 is parallel to B1, and which is what we see here, which is jog or edge. It's a jog type dislocation and it has edge character. Now, if you look at this dislocation, it would want to move in this direction, and this is the glide plane. And for this dislocation, this is the glide plane. So overall, when this dislocation wants to move, it can easily move along with the step size, step S2. Similarly, for S, there is nothing like S1, so we need not to worry about it. So in this case, we can say that step that is formed on dislocation 2 aids in glide. This will become clear when we look at case 3 and case 4, where we have screw dislocations and where you would see that the steps that are formed do not aid in dislocation. So this is case 1, where we have two edge dislocations, but their Burgers vector are perpendicular. Now let's look at another case. Case 2, again this time we are looking at two edge dislocations, but as you would see, their Burgers vector are parallel. So yes, it is possible to have two parallel edge dislocations and they are on two different planes. So to begin with, let me draw the planes. So I have already drawn the two, the before and after planes. And now I will draw the dislocations on them. So this is my first dislocation, and I will term it B1E, edge dislocation, and this one is B2E, and this one is moving in this direction. So eventually it will intersect. And the step that will be formed on B2 will be equal to the Burgers vector. So I can draw on the direction. So this is the Burgers vector, this is the Burgers vector. So both the Burgers vector are parallel. So it will form a step which will be in this direction and of magnitude equal to B1. And in this one, step will be formed in this direction, which will again be of the magnitude B2. So how does it look like after it has intersected? So for that, let me draw a dashed line over here. And as mentioned, this will have a step, which is this is the step that will be formed on B2E. This is B2E. And there will also be a step formed in B1E. Again, it will be in this direction. So this is S2 and this is S1. And S2 is, of course, the magnitude is equal to B1 and S2 is parallel to B1. On the other hand, S1 is magnitude is equal to B2 and S1 is parallel to B1. And as you can see, both of them are kinks. So it is in the same plane, so both of them are kinks. S1 and S2 are kinks. And as you can also see that this is the Burgers vector, this is the Burgers vector, so it is along the dislocation line. So both of them are screw character. So both of them are screw character. And this dislocation would want to move in this direction and the kinks would move in this direction. So overall it can move and help aid in the movement of the dislocation along its original glide plane. Therefore, both aid in glide. So in this case also, there is no problem with the steps that are formed. They do not cause any hindrance to the movement of the original dislocations. Now we will add a little bit of complexity. We will now have a screw dislocation also into the mix of things. So case 3, we have edge and a screw dislocation. So here it is a little bit difficult to, or I shouldn't say difficult, But here I will have to make certain assumptions because screw dislocations do not have a defined plane as per se. So we will assume that there is a certain plane, and accordingly we will define whether what we are forming, what we are getting as the steps are kink or jogs. So let's say that this is a plane which has screw dislocation over here. So let me draw it like this. And let's say this is a edge dislocation like this. So this has the Burgers vector, of course, like this. So I will name this as 1 B1E, and it must have line Burgers vector along the line direction. So it is B2S. And I will assume that this one is moving. So this one has a defined plane. I don't need to define it. For this one, I will assume that this is the plane on which it moves. So what happens to this after the intersection? And again, let me draw. So here the Burgers vector is along this direction. So the step will also be formed along this direction. And the Burgers vector for this one is along this direction. So the step must be formed in this along this direction. So how would it look like? Let's see. So this is B2S and the edge dislocation, which was like this. But now, because of the Burgers vector for this one, it has to move out of the plane. And therefore now it will, part of it is in a different plane. And this is its Burgers vector B1E. So this is the jog. Now you can see that this is the line, dislocation line, and the Burgers vector is like this. Therefore, this is edge in character. Now over here, this is the dislocation line, and this is the, this is the dislocation line, and the magnitude, of course, we will look at in just a moment. And this is the Burgers vector. So this is also edge in character. And this is step 1, this is step 2. So S1, will just for the sake of completeness, we will write S1 is equal to Burgers vector B2. S1 is parallel to B2. S2 is equal to B1 magnitude wise, and S2 is parallel to B1. And in this case, what do we see is that this particular dislocation that we see over this one, this step, this dislocation wants to move in this glide plane, and for this is the glide plane. So it can move along with the rest of the dislocation, and hence it can aid in glide. However, for this one, what we see is that this is the dislocation, and this is the dislocation, this is the step, and for this was the original plane on which it wanted to move. But for this one, this overall, let me draw it over here. So this highlighted plane is the glide plane for this step S2, but that is not the plane onto which the dislocation to screw dislocation wants to move, and therefore this will not aid in glide, and this will become a sessile. This step will become sessile. So this is what we had mentioned earlier. So this is sessile, does not aid in glide. On the other hand, this is glissile like all others. So I have not mentioned explicitly, but when I say that it aids in movement, it means it is glissile. So that is case 3. Now there is still another case that we can look at, and which will be even more interesting. It would be when we have two screw dislocations moving with each other. So we will have two screw dislocations, and let's draw it like this. So one is over here with Berger vector like this, and the other one is like this. Now let's say that this one is moving along this direction. So this has a step vector. This has a Berger vector like this. So it will form a step along this direction. And for this one, there will be a step along this direction. So after intersection, this is how it should look like. So this is the step, and clearly part of it was moving on this plane, and part of it has moved to the bottom plane, and therefore this is a jog. On the other hand, this one, we will assume that this is the glide plane for this. So and for this one, this was the glide plane. So this has clearly moved out of the glide plane. On the other hand, for this one, so this still remains in its glide plane, and therefore it is a kink. So this is S1, this is S2. S1, magnitude wise, it is equal to B2, and S1 is parallel to B2, and it is a jog. And S2, magnitude wise, it is equal to B1. S2 is parallel to B1, and it is in the same plane, so it is a kink. And here, as you can see, there is the line dislocation, and this is the Berger's vector. So this is jog, and therefore, and it is also a edge dislocation type jog. And over here, there is line dislocation. This is the Berger's vector, and this is the line vector. So it will also be edge. So in this case, both of them, for a screw dislocation, whenever there will be step, it will always be edge dislocation. And like I said, that this is in the same plane, so this can move, and hence it can allow this dislocation to move. Therefore, it aids in movement, but this one is sessile. Okay, so yeah, I missed writing down the character of the steps over here. So this is over here. If you look at this one, this is a jog, and if you look at this one, this is also a jog. So, and this one is also an edge dislocation. So let's complete this, that this is also a jog and it is an edge dislocation. Here we have written both of them are kinks and they also are screw character. And here we have written jog and edge character. So we have summarized all these, and we can actually make a table to put this all at one place where we will be able to identify whether it is a jog or a kink, whether it is screw dislocation or edge dislocation, and whether it is glissile or sessile. So in case one, when I say dislocation one, it means the step on the dislocation one. It is, we have seen, it is jog and it is of edge character. For dislocation T, we saw that it is not applicable because the step was formed along the line direction, which doesn't mean anything. For case 2, the step was kink and it had screw character. In fact, both of them had screw character and they were kink. For case 3, we saw that it was a jog for dislocation 1 and it has edge character, and we saw that for dislocation 2, which was a screw dislocation. So for the screw dislocation also, we saw it is jog and edge. For case 4, where we had both the screw dislocations, we saw that for the first one, it is a jog and edge, and for the second screw dislocation, it is kink and edge. Here, it must be specified that we have made certain assumptions about the glide plane. So, glide planes were assumed. And the only steps which we saw were not glissile are this one and this one. All the others where I have not written S, S means sessile. Meaning does not aid in movement of the original dislocation. So all other steps do aid in movement of dislocation. So what we see again here is that these can form or can pin the dislocations. And when you pin these dislocations, then again, you can have that when you keep applying the stress, the dislocation length will increase and eventually it will form a loop and loop around, and extra length of dislocation will be formed and it will at one point break away. And then again, original dislocation will stay there. And if you keep applying, and this is how the dislocation density keeps increasing. And the other part that we said that whenever there is a step formed, there is a cost, energy cost. So what do we mean by that? So let's look at that part also. So when so this is something we have already mentioned. And based on this, what we can write is that if we know that energy per unit length of a dislocation is given by alpha GB square, but if we want to know the total length, if we know the total length, we can put it there, which is in this case is equal to B, and therefore it becomes alpha GB Q. So energy of step is equal to GBQ. So this is the energy cost of adding a step. So whenever there will be dislocation intersection, this much additional energy needs to be provided, which means next time you will have to apply higher stress for dislocations to move. So overall, there are certain things that we can summarize regarding the intersection of the dislocations. So let's put those in words over here. So whenever edge dislocation and edge dislocation intersect, it gives rise to glissile step. That can aid in motion. When you have a step in the screw dislocation, which is jog in character, then it is sessile. And also it is jog means it will be edge type. On the other hand, if the step is kink, then it would mean that it is screw dislocation, and it would also mean that, sorry, even the kink would be edge character, and it will be glissile in nature. Edge dislocation, we have said that are always glissile in nature, but about the nature of the steps, it can be either jog, which will has edge character, or it can be kink, which can have screw character. So screw dislocations always give while for edge dislocation, it can be both edge or screw, depending on whether you are forming jog or kink. So in this lecture, we have looked at the step formation, intersection of the dislocation, which leads to step formation. And some of these steps can be sessile, which means they can pin the boundary, which can pin the dislocation, and hence those pinned part can, as we have seen earlier, can lead to Frank-Reed sources. There can be other nature of pinning of dislocations also, but this is one way that the dislocations can get pinned. And there is still another way of pinning of the dislocation, which is the point where we move on next. And that is called dislocation locks. So what happens is that in dislocation locks, certain dislocations get or intersect, not intersect, but interact and result in a dislocation which is on a plane where it cannot move, and therefore it becomes locked. It can either move away nor it will give way for other dislocations, and therefore all the dislocations would then pile up over there. And it is in this process that we see a dislocation lock. So in this context, let's look at one particular type of dislocation lock, which is called as Lomer-Cottrell lock, which is observed in FCC material. So to understand this, first list up all the dislocation slip planes for 111, all the dislocation Burgers vector for 111 slip plane and 11 bar 1. So we know there are 4 different slip planes in FCC. So out of these 4, let's first list up, take up only 2 first, and the same thing can be extended to the other pair of slip planes. So here we are taking 111 slip plane and 11 bar 1 slip plane. So let's call B1 equal to A by 2, 1 bar 1 0, and of course the negative would also be the Burgers vector for this particular plane. If you remember the Thompson's tetrahedron, it has 3 directions, so there must be 3 Burgers vector and the negatives. And you can check that the dot product of this would give you 0. So these are the Burgers vector for 111, and these are the Burgers vector for 11 bar 1. One zero one. Again, you can check that the dot product of this and this would be 0, as you would expect. Now let's say that 2 of the Burgers vector, 2 of the dislocations with these Burgers vector intersect. So there is no meaning of dislocation intersection within a plane. Let's say that there are dislocations which intersect, one dislocation from here and another from here. So let's take a combination of B1, which can be positive or negative, and B5 or B6. So we are taking this one and this one. So both the dislocations are moving in their own plane, but they may intersect, or there may always come a line which will be common to both, and that is where we are looking at. So B1 plus B6, what you would see comes out to A by 2, 1 0 1, which is nothing but B5, because B1 is same as B4. So some of these combinations would result in the Burgers vector, another Burgers vector of the same slip plane. Similarly, if you look at B1 plus minus B5, you would get A by 2, 0 bar 1 equal to minus B6. Now let's look at B1 plus B5. And what you will get is A by 2, 2 bar 1, 1. and another one is B1 plus minus B6, and this would be A by 2, 1 bar 2 bar 1. So this is something you can try on your own, and this one does not mean anything. These two, if you look energetically, it is not energetically favorable. And there is a cube I have drawn here. I will use this a little later. So let me just pull it down for the time being. So now what we see is that combination of B1 with B5, B6 is not leading anywhere. In fact, if you do the same thing with B4 plus B2, B3, it will not lead to nothing interesting. But now let's move on to another combination, which is B2 and B5. So B2 plus B5 or B6. So this gives us A by 2, 0, 0, 2. B2 plus minus B5. These are all possibilities. A by 2, bar 2, 0, 0. B2 plus B6 and B2 plus minus B6. Now, let's look at it energetically. If you compare it, I'm not going through the overall action, but if you compare energetically, what we mean is doing the B square, comparing B square plus B square and the B square of this one. What you would see is that this is equal. So this is equal, this is equal. This is not energetically favorable, but this one is energetically favorable. Meaning if two dislocations with one with Berger vector B2 gliding on plane 1, 1, 1 and another dislocation with Berger vector minus B6 gliding on plane 1, 1 bar 1, they happen to intersect at some place, interact or react at some place. The most suitable word would be react, because they are now combining the two Berger's vector, combining to form this Berger's vector. Then this Berger's vector is actually energetically favorable. So this dislocation would indeed be formed. So this is something that we need to look further. What does it mean? What will be the glide plane of this particular dislocation? What would it be on its native plane, meaning one of the 1, 1, 1 plane, and so on. Okay, so let's analyze this resultant dislocation. First of all, let's find out let's try to visualize this dislocation. So it is on two different planes, 1, 1, 1 and 1, 1 bar 1. So let's say this is one of the planes, and this is another one of the planes. And over here you have some dislocation with line vector U1, and the Berger vector is B2. And over here you have a dislocation with line vector U2, and the Berger's vector is B5. And somewhere over here, these two combine, and the line on which they will combine is this one. So we can define or understand what is the line vector of the resultant dislocation by finding the intersection of these two planes. What are these planes? Again, these were 1, 1, 1 and 1, 1 bar 1. So if we take the cross product of these two, we will be able to find the line vector, which is the UR. So UR is equal to 1, 1, 1 cross 1, 1 bar 1. And I have taken it as a vector here. So this comes out to bar 1, 1, 0. So this is the line vector of the dislocation, and this is the Burgers vector. So this is Burgers vector, and let me write down the Burgers vector again here. And this is the line vector. So if these are the line vector and Burgers vector, what is the plane on which it is lying? The plane on which it is lying is equal to BR cross UR, and you would see that this will happen to be 0, 0, 1. But is it a glide plane? And the answer is no. So it is not a glide plane. So let me draw it. So it would look something like this. So this would be the glide plane over here, and the resultant Burgers vector would be probably somewhere over here. So this is the line vector, the Burgers vector, and this is the glide plane, which is 1, 0, 0, 1 in this particular case. And the question is whether is it a glide plane in FCC, and the answer is no. What does that mean? It would mean that this dislocation would not move. Dislocation is glacial. Now with this information, go back and look at this. This dislocation was very nicely moving onto this plane. This dislocation was also very nicely moving onto this plane. But somehow they happen to be here at the same time, and therefore they interacted, and actually the more appropriate term is reacted, resulting in this Burgers vector BR, resulting in a line vector UR. And therefore now it is locked into this glide plane, which is not a native glide plane, and therefore it cannot move. Now any other dislocation coming from behind will now not be able to move past this, and therefore it will act like a lock. This cannot move, and it will remain fixed over here, and it will also not allow any other dislocation from this direction or that direction to move further, and therefore it will lead to, you can say again, some type of pinning of the dislocations, and this again leads to strengthening of the material, hardening of the material. Now this is not just one particular combination which will result in a lock. For a given set, you can have actually two sets of Burgers vector combination which can result in the locks, and it is in this respect that let's look at this cube that I was showing you earlier. So what this cube is showing you is basically the 1, 1, 1 planes. So let's draw it again here. So this is 1, 1, 1 plane, as you can see, 1, 1, 1 family of planes. And to be precise, this one would become 1, 1, 1, and this one would become 1, 1 bar 1. Now here, these would be your Burgers vector. So these are the edges. So this is a Thompson's tetrahedron in effect. So these are the one Burgers vector on a second Burgers vector, third Burgers vector for 1, 1, 1 plane. And this is 1, 1 bar 1 plane. And this is one Burgers vector for 1, 1 bar 1. There's another Burgers vector. This is another Burgers vector. Now let's look at this in a much more closer way. Now let's say that there is a dislocation which has a Burgers vector which is moving on 1, 1, 1 and has a dislocation Burgers vector like this. And at the same time, there's another dislocation on 1, 1 bar 1 which has a Burgers vector like this. Now, what will be the resultant vector for this one? The resultant vector would be this one. And therefore, this is equivalent to saying this is the resultant Burgers vector. Now, if this is the resultant Burgers vector, and which is the line vector, because this has to lie on the common line, therefore this must be the line vector. So if this is the Burgers vector and this is the line vector, then this must be the glide plane for that particular dislocation. And as you can see, this is a 001 type of plane, and therefore it is not glissile, and the dislocation that has been formed by this, or lock that has been formed by this, would be sessile. It would be a lock. And it is here that when you look at this from this point of view, you can clearly see that the same combination can also be obtained by a dislocation here and a dislocation over here. So these two would combine to give you the same thing over here, and it will be the same final resultant Burgers vector and the same final resultant plane, and also the same final resultant line vector. So both these sets would give you the same dislocation lock. Now this is only for 111 and 11 bar 1. You can go ahead and do the maths for other set of planes, 111 and the other one, whatever the family of this. So there are 4 families. You can take pairs of any of these and you will still get the same thing. You will be able to get a lock. So this lock is not very uncommon. It can be commonly found in the FCC type of system. So this again gives you an idea that when the dislocations move, when the stresses are being applied, the dislocations move and they will intersect and interact and react, and this will lead to dislocation multiplication, which is what leads to the hardening of the material. And also the back stresses when there are locks formed like this, or when there is a pileup, all these lead to strain hardening of the material. So if you look at the stress strain curve of a material, this should, and on this axis, let's say we have percentage cold work, and this is stress, this is strain. So it would look something like this. And if you increase the amount of cold work, then the stress, the yield strength and the tensile strength increases, but at the same time, ductility decreases. And at some point, it will become very, very brittle. So this is how the yield strength would increase. So if I were to mark the yield strength, probably the yield strength is increasing like this. And at the same time, ductility is decreasing. And this is what, with increasing cold work, straining and internal resistance. So there are now more dislocations, more backup stresses. So internal resistance increases. And hence, applied stress needs to be increased. And this is what we term as strengthening, strain hardening. Okay, so with that, we will close this lecture. And in the next lecture, we will summarize all the strengthening mechanism that we have looked at. Thank you.